All right. So a star with a surface area of 5,200 kelvins has a radius of 6.5 times 10 to the 8th meters and is 1.7 times 10 to the 11th meters from a planet. Assume the star is a perfect black body. By the way, that's coded word language for the emissivity of the star is 1. Okay. Perfect black body. Calculate the intensity of the radiation in watts per square meter incident on the planet's upper atmosphere. So there's 2 steps to this. The first step is that we are going to figure out the luminosity of the star, which is just the total power output of the star, right? So power output is what E sigma area temperature to the 4th, right? So let's figure that out. It says that it's a perfect black body, so that's, and this, by the way, this is going to be a tremendous number. Okay, so the emissivity is 1. Okay, and then it's 5.67 times 10 to the minus 8th, and that's watts per square meter, Kelvin to the 4th, right? And then what's our area? Well, the area, the surface area of a sphere, wingy, is right there, right? So that's going to be 4 pi times 6.5 times 10 to the 8th squared, right? So that's my area, right? I'm using the surface area of this star, right? And then 5,200 to the 4th, right? So these are giant numbers. We expect this to be tremendously large. Okay, so I've got 1 times 5.67 times 10 to the minus 8th times 4 pi times 6.5 E8, 6.5 E8 squared times 5,200 raised to the 4th power. All right, I'm getting that this is 2.201 times 10 to the 26th watts. That is the total power output. By the way, this is called the luminosity of the star. Okay. Now, the second part of this is, like, I don't know how you're supposed to do this, but I found this on one of our tests, so it's a valid question, right? Okay. But if you go to section D1, it's on the very back. If you go to D1 in the back, like this is like astrophysics, right? You'll find the formula that the brightness of a star, and this is the intensity in watts per square meter, is the luminosity divided by 4 pi d squared, right? Now, where this comes from is, let's imagine that we've got a star right here, right? It's gonna, if we're at some distance from that star, right, all of the energy that star is creating is being spread out over an area of 4 pi r squared, right? So that's what it is it's basically this is the power output, and we're going to put this number in there, right? And it's divided by the area of a sphere that is at the radius we are at, okay? So let's do this, right? So the intensity, the watts per square meter, right, is going to be this 2.201 times 10 to the 26th watts divided by, okay, and then it's going to be 4 pi, and then we are 1.7 times 10 to the 11th meters from the planet, 1.7 times 10 to the 11th, and then square that, and this is meters, right? So we'll get watts per square meter, okay? So I'm going to take this number that's on my calculator, go divided by parentheses 4 pi 1.7 E11 squared. I'm relying on this calculator to do the right thing, which makes me nervous. I get 606.0735 watts. We have 2 sig figs, so really we'd have to say about 610 watts per square meter. Right? I'm going to go with 606 or something like that. Okay? So again, the first step to this thing is you want to figure out the total power output using radiative heat transfer, right? The area is going to be your 4 pi r squared of the surface of the planet, right? And then you step back, and that power is going to be spread out over a much bigger sphere, right? The sphere that is where this planet is, right? The sphere that is the same distance, right? It has a radius that is the distance to the planet, okay? All right.